Hi everyone, I'm Mikhail. Welcome to the Dark Wire Labs YouTube channel, where we break down network technologies and bring them to life with real code. In today's video, we are building a functional HTTPS load balancer from scratch using Go programming language. As usually, we aren't just talking about theory, we are going to implement TCP-level balancing and TLS offload, package them into Docker containers, and demonstrate how traffic flows through a custom-built network. So, what is a network load balancer? At its core, a load balancer is a traffic cop. Its job is to sit in front of your servers and distribute incoming requests so that no single server gets overwhelmed. This improves the availability and scalability of your application. Now let's compare two modes of a load balancer, TCP and TLS offload. TCP load balancer operates at layer 4. In this mode, the load balancer acts as a transparent relay. It does not care about the content of the data, whether it's HTTP, SQL, or even custom binary data. It listens to incoming TCP connections from clients and establishes outgoing TCP connections to the backend servers, just copying bytes from one connection to another. A load balancer typically checks health of each backend server to move the load away from failed servers. Load balancer can use round-robin or more complex algorithm to distribute the load. TLS offload mode operates at layer 7. In this mode, the load balancer is a terminator. It acts as the final destination for the encryption and a fresh starting point for the backend request. A load balancer presents its certificate to a client, and they negotiate keys and establish an encrypted tunnel. The client sends an encrypted HTTP request. The load balancer decrypts this into plain text. Because the load balancer now has the plain text, it can look at the headers. It sees the path, user agent, and cookies. Load balancer creates a brand new HTTP request. It might add a header like x forwarded for, so the backend knows who the real client is. The load balancer sends this plain text HTTP request to the backend, so the backend server doesn't need to waste CPU cycles on encryption and decryption. In some scenarios, load balancers can establish encrypted HTTPS connections to the backend. For our today's demonstration, we are building three components: the backends, two Go-based HTTP servers that identify themselves as server A and server B, the balancer, a Go application that can switch between a raw TCP proxy and HTTPS reverse proxy, the network, a private Docker bridge network that isolates our backends from the public internet. We use Docker Compose to orchestrate the environment. This allows us to define our infrastructure as code. So step 1. We generate a self-signed TLS certificate so our load balancer can handle HTTPS. Step 2. We spin up our containers. Step 3. We test. I've asked Google Gemini to generate all code for me, including Docker and Docker Compose files. Let's look at what we've got. So we've got the load balancer code. That's the code. Pretty simple. So it implements two functions. One is TCP load balancer, and another one is TLS load balancer. And it expects an argument on the start which mode it should operate in. Then the load will be distributed between two backend servers. And of course we need to supply the server certificate for the load balancer and the private key. This is listing of the backend server. The backend server simply listens to incoming HTTP connections, and yeah, so we specify the port as the argument and the server name as the argument. And the server will just respond with this message stating what's the name of the server and what's the port. This is how Docker Compose file looks like. So here we deploy server A and server B for the backend, and we deploy the load balancer. So we specify ports that we need to publish. We specify the volumes for certificate and the key, and here in the command line we need to specify mode, whether it's TCP or TLS, and the port. So first we'll start the deployment in TCP mode to test it. Before we run the container, we need to generate certificate and the key. We use OpenSSL for that inside the container. So we've got these two files. Now we can run this deployment. Okay, as we see, all three container instances have been built and are running. The load balancer is listening on port 8090 and forwarding it to backend 1 and backend 2 on port 8080. So we can simulate a simple HTTP request for this. Since the Docker environment is running on my local machine, I can do it this way by just specifying HTTP localhost and the port 8090 where the load balancer is published. Okay, so now we've got reply from server A, and in the log we also see that the server A received HTTP GET request. If we update the page, we get response from server B, because our load balancer is using a round-robin algorithm to distribute the load. In fact, we could use curl for the same. Now I want to run a packet capture on the load balancer to see how this packet capture looks like. So I'm going to my Docker desktop, the terminal on the load balancer. Just to confirm, yeah, that's the load balancer because I see a process running here. Let's run TCP dump in a file. Now let's send a request. We stop or capture. We've got new file. So we just need to pull it out from this container and analyze it with Wireshark. A moment, please. Okay, that's the capture. We may see some keep alives or acknowledgements from previous connections. We basically don't want them, so I'll just filter it for one specific TCP stream. Click on follow the stream, and you get this. And just to validate once again, that's the IP of the load balancer. So the load balancer IP was 172.18.04. It will be destination. We see TCP SYN, SYNAC ACK, that's TCP three-way handshake. Then HTTP GET request, server response. In this case, that's a load balancer response. And in the body of the message, we see hello from backend server B. Now let's go to the other TCP connection, because this connection, it represents communication between the client and the load balancer. Now we look at the TCP connection representing the load balancer and the backend server. Here the load balancer is initiating connection, backend server is responding, load balancer is just sending the same HTTP request, just relaying whatever I sent from my client. As you can see, even the user agent is kept the same. It's cool. And the backend server is responding with the code. So that's a pretty simple example. Now we stop this environment. We update the Docker Compose file to change mode to TLS and change port to 8443. We redeploy everything. Right. Now you see load balancer started in TLS offload mode, listening on port 8443 for HTTPS and forwarding it to the same backend 1 and backend 2 on the same ports. Okay. So now we need to try HTTPS connection. Yeah, the browser will throw a warning about certificate because we generated self-signed certificate. You either need to add it in your trusted certificate store or to get a proper certificate signed by some public CA to avoid this warning. But for our test, that's okay. We accept the risk and we are getting hello from backend server B. I think we need to open another window or maybe try it from I think we need to fix the certificate warning. try it in another browser. Actually, I'm not sure why we are always getting it from server B, as it should. Ah, okay, yeah. It's actually distributing it, so I was wrong. I think for the first attempt it was always connected to server B, but then it was going to server A. So I just had to refresh it. Yeah. Okay, here it's stuck on the server A. I guess that's could be something related to the keep alives. But that's okay. Working fine. Okay, now I want to capture traffic. I go to the Docker. I run TCP dump. Okay, now I need to pull the file. Opening it in Wireshark. What we see here. I think this, okay, I guess this connection, this encrypted connection between my browser and the load balancer, it stays persistent. So we need to capture it once again. I'm going to open new tab. Okay. Yeah, now it should be fine. Follow the right TCP stream. This is not the right TCP stream. This is the right TCP stream. Okay, so what we see here? We are seeing here TCP three-way handshake between my computer and the load balancer. Then we see our client is sending client hello to the TLS 1.3 negotiation. Load balancer is responding with server hello, and then the load balancer is it's presenting its certificate and sending some application data, but it's encrypted. We can't see it. Actually, there is a way to see it we could export our SSL session keys from my browser and import it in Wireshark, and then we will be able to encrypt all these packets. Let's take a look at the connection from the load balancer to the backend server. So the load balancer, it establishes the TCP connection, three-way handshake with server B. This is the server B, and sending HTTP GET request, and the server is responding. You see it's server B. Yeah. So the server is responding, and then the load balancer is relaying this data back to our browser, but already inside the encrypted tunnel. Alright, that's it for today. I hope you enjoyed this video. See you next time.